Hi everyone, I'm Zhang from Chalmers, presenting our work on collision-free navigation of mobile robots via Quadtree-Based Model Predictive Control. I'll start with a description of the general problem and the basic concepts. In the collision-free navigation problem for mobile robots, while avoiding simple obstacles is well established. The robot may face obstacles with non-convex shapes, not to mention complex environments with time limitations and many non-convex barriers, for which we seek a safe and efficient navigation approach. It is common to recognize the map as an occupancy grid, where it is discretized into cells with free or occupied status. To increase the efficiency and precision, the occupancy map can be built in an incremental and hierarchical way. So areas are continuously divided until they are purely free or occupied, or the maximum depth is reached. This can be organized as a quadtree. By merging the safe areas, a concise representation of the map is obtained. With the map representation, we fall back on the obstacle avoidance. Model predictive control is an optimal control method that handles local planning and control. It predicts the nominal future states, then checks constraints and the objective for each step to obtain the best local trajectory and actions. However, as an optimization method, it suffers from local minima and computational cost, especially for complex environments. In our approach, instead of focusing on formulating the obstacles, the idea is to collect safe areas and ensure that the robot stays in these areas. Based on this, I introduce our safe area-based MPC pipeline. First of all, we generate the quadtree of the occupancy map and merge safe areas for stable and efficient navigation. We also check the connectivity so that only safe areas leading to the goal position are considered. Then, we calculate both a new reference trajectory and new constraints for MPC, which gives us the final safe area MPC formulation. We compare our method with traditional obstacle modeling MPC, learning-based DQN, and sampling-based AA in different scenarios. The result shows that the proposed safe area MPC achieves the best performance and efficient computation. This work is partially inspired by our collaboration with AB Volvo, during which we developed a real-time visual system that captures the environment in the factory. Based on the visual system, we can obtain the free areas for mobile robots. Combining with predefined drivable areas, we can have the safe areas for the proposed framework. To conclude, we proposed a safe and efficient navigation framework, integrating Quadtree-based safe area generation and MPC. We also incorporate safe area constraint in the MPC formulation. In the future, we want to implement a dynamic quadtree for dynamic obstacles, and also to have real-world experiments in industrial environments to validate the method. Finally, I gratefully acknowledge the support of the II student and Young Professionals Paper Assistance Program. Thank you.